Welcome back to Segment 5 of the informational workshop for Chapter 1, An Introduction to Geology. During this segment of the informational workshop, we're going to be talking about systems, about Earth's spheres, and about feedback mechanisms. I think this is going to be a really interesting section for you to think about, and I think as we go through the section, you're going to find out that you already know a lot of this information. If you'll think back to some of the studies that you did of biomes in biology and some of the studies that you did last year in chemistry and physics, I think you'll recognize some of these topics and some of these concepts. Let's start out with a question. So on this first slide, we have a picture of a car and a picture of the Earth. And the question says, if we're talking about a systems approach, so think about different systems that might exist in each one of these objects, what do a car and the Earth have in common? I'm going to give you a couple of minutes here to pause this video and write down your thoughts. Write down some of the things that the systems in a car might have in common with systems in the Earth. You can make notes right on your packet notes sheet. So go ahead and pause here. On our next slide, we're going to be considering some of the vocabulary associated with systems. Now, let's just take an aside here to talk about why it's important to understand this vocabulary and why it's important to understand what a system is as we think forward towards what we're going to be studying during this year in geology. So during this year, we'll be studying lots of different systems that actually operate in and on the Earth. And these systems interact with each other. There are feedback mechanisms between systems and within systems. And it's important for us to be able to understand not only the individual smaller systems and cycles, but also to be able to understand their impact on each other and how they all collectively add up to form the Earth system. So that's our big context and our big picture. So let's get some of this vocabulary down. Here we see the definition of a term called a natural system. And if we'll look at this definition quickly, it says it is a functioning set of natural components which are powered by energy and which interact with each other through a complex set of feedback loops. So that's a pretty hefty definition. And what I would like you to do is I would like you to go ahead and underline words in that definition that you think are key terms or key words to what a natural system really is. I'll give you a second to do that. So here are some of the words I think you might have underlined. I think you might have underlined set and natural and energy and interact and probably feedback loops. Those are some of the things that we need to consider when we try to determine if something is a natural system or not. Well, let's take a look at the picture that's shown here. So here you can see a picture of a seahorse. And if you look way in the back of the seahorse, you might even see your geology teacher there. This is a picture taken this summer when I was scuba diving in Florida. And this is a little seahorse. And as I was watching him, as he was swimming from one little piece of coral to another, or one rock to another, I was thinking about what the world is like that he actually lives in, and how that particular world is a natural system. What are some of the components of that natural system? So that's a kind of a complex question to answer if you haven't experienced the environment that he lives in. But let's stop for a second to think about the components of the natural system in which we live. So I'd like you to go ahead and pause the video for a moment here. And after you've paused it, to the right of your slide on your notes sheet, I would like you to make some notes about the components of the natural system in which you live. What are some things that are critical to you being able to live and exist in this natural system? Rejoin you in a minute. Go ahead and pause. Now that we've talked about natural systems, let's talk a little bit about open and closed systems. And I think it's easier to start with closed systems, so that's what we're going to do. Here's the definition of a closed system. Closed systems are systems that are self-contained in terms of matter. Now, there are lots of examples of different closed systems that we could give, but the example that I've given you here to think about is the example of a nuclear power plant. So in this picture, you can see that all of the components that are part of the nuclear power plant are contained within those various loops. There's a pink loop, there's a blue loop, and everything that happens within that nuclear power plant is contained within those loops. There is nothing on the outside that comes into contact with things that are on the inside, essentially. So think about other closed systems. Can you think of any examples? Write them down to the right of the slide. I'll give you a second to do that. Now that you've written down a couple of examples, I'd like you to think about things that all of those examples have in common. What is it that makes all of them closed systems? At this point, you're going to want to pause this video, and you're going to want to write down a working definition for yourself that describes how a closed system is different from the example given earlier of the natural system in which we live. What makes a closed system different from this system that we live in? Go ahead and pause the video. Thanks for rejoining me. We'll talk about open systems at this point. So an open system is a situation where the systems, both matter and energy, flow in and out of a system. Very different from a closed system. So in contrast to the earlier picture that you looked at of the nuclear power plant, think about this big environment. Here you see a beach. What various systems can you see acting here? You know there's weather, you can see the clouds. You know there's water, you can see the waves. You know there's the system of the solid earth, you can see the sand and the rocks in this case. You can see some examples of biology here, not only the humans, but you can see some seaweed that's washed up on shore. What is different about an open system? How can you distinguish an open system from a closed system? Take a minute here to write down your thoughts about how open and closed systems are different from each other. And once you do that, be ready for your quick mastery check. It's coming up next. Okay, here's your quick mastery check for segment 5. In this mastery check, you may choose any system to describe. You decide what the system might be. It's up to you. You pick any system. Once you've chosen a system, determine which type of system it is. Is it an open system or a closed system? And explain how you know which type of system it is. You might want to describe the component parts as you describe how you know it's an open or a closed system. Go ahead and pause here. Segment 6 coming up is going to talk about feedback mechanisms and the Earth's spheres. Welcome back to Segment 6 of the Informational Workshop for Introduction to Geology, Chapter 1. In this segment, we're going to be taking our understanding of systems and expanding it to talk about Earth's spheres and then feedback mechanisms within those systems and spheres. Again, this is a topic that we'll be coming back to throughout the school year, so it's important for us to get a solid foundation in terms of the vocabulary and understanding of the concept. So think back to your idea about natural systems. And as you listed out the natural systems and components of the natural system that are in the world around us, I bet that you listed out different components from the different spheres that are shown here on this slide. So Earth is broken down into 4 main spheres. And the 4 main spheres are the hydrosphere, the lithosphere or geosphere, the atmosphere, and the biosphere. Now you've had some experience with some of these spheres in your past science classes, and I bet that you could come up with a definition for each one of these spheres. So I'm going to ask you to go ahead and pause this video for a moment, and I'm going to ask you to write what you think each one of those 4 spheres includes. Look carefully at the words: hydrosphere, lithosphere or geosphere, atmosphere, and biosphere. Now if you need some help with this, I'm going to encourage you to jump out and take a look at your textbook. Pages 15 and 16 talk about the 4 spheres. But I think you can really handle this on your own. So go ahead and pause. Rejoin me when you're finished making your notes. Great. So I'm sure that if you started with hydrosphere, you recognized the prefix hydro, and you knew that that had to do with water. So hopefully you listed some things about Earth's oceans and lakes, rivers and ponds, all of those being part of the hydrosphere. But as you'll find out in geology, there are other components of Earth's water sphere or hydrosphere, especially the component of groundwater and of ice caps, glaciers, that become very important as we discuss the hydrosphere. Those are concepts we'll be studying later on in the winter. The idea of the lithosphere or geosphere. This is Earth's solid materials, terra firma, solid Earth. We will be studying the geosphere in great depth, starting out after this chapter with Chapter 2 as we look at plate tectonics, earthquakes, volcanoes, deformation of the Earth's surface into folds and faults, all components of the geosphere. We'll be looking at natural resources and many other things. The atmosphere. Earth's atmosphere. We'll be talking about the atmosphere of the Earth later on in the school year when we consider climate change or climate disruption. And finally, the biosphere. The flora and fauna that make up Earth's biosphere. You've done a lot of study of this in your biology classes in the past, and you should be familiar with some of these things. We'll be talking about them just tangentially when we talk about Earth's materials, things like fossils and geologic time. Let's go on to the next slide, and let's consider feedback mechanisms. At this point, I would like you to pause the slide, and I would like you to jump out to this website that's called Daisy World. So you're going to click on the blue link where it says Daisy World, and you're going to be visiting a place that is inhabited by black and white daisies. What I want you to look at as you allow these feedback mechanisms to take place is what happens when there is a positive or negative feedback. What happens when the white daisies take over the world? Why do they take over, and what happens as a result of them taking over? Likewise, when the black daisies take over, what happens and why? So as you watch the Daisy World website, go ahead and make notes to the right of this slide about the feedback mechanisms that are operating in Daisy World. Pause here, jump out to Daisy World, and then rejoin me, and we'll talk specifically about feedback mechanisms. Welcome back. Let's start talking about feedback mechanisms with positive feedback mechanisms. So anytime that you see a change in something, you'll want to think about whether it is a positive or a negative feedback mechanism. In the case of a positive feedback mechanism, that is a mechanism that enhances or drives change. For the case of this example, let's consider the picture here. In this picture, you can see a sunny day, relatively clear sky, and you can see a polar bear that is standing on top of a chunk of ice, and the ice is floating in an ocean. Now let's consider what's happening in this picture. If you think about it, the sun's rays are impacting the ice, the sun's rays are impacting the clouds up in the sky, the sun's rays are impacting the ocean water, and they're impacting that white-colored polar bear. Now think for a minute about what happens that's different when the sun's rays hit off of the white fur of the polar bear or the white ice versus the much darker colored ocean water. Which surface, the lighter surface, ice or the polar bear, or the darker ocean water, is going to actually reflect the sun's energy? And which surface is going to absorb the sun's energy? Now, if you answered that the polar bear and the ice will both tend to reflect the sun's energy, you're right. And that the ocean water will tend to absorb it, you're right again. But what happens in that case? The ocean water starts to heat up in response to the increased incoming solar radiation. And as that ocean water heats up, what do you think happens to the ice that polar bear is standing on? If you said it melts more rapidly, you're absolutely right. And as that ice melts, and as the other chunks of ice that are surrounding this piece melt, there is less ice for the sun's energy to reflect off of, and more water for the sun's energy to be absorbed by. So what will happen is that the water will continue to heat up. As it heats up, it will melt more ice, which in turn will create more water to absorb more energy, which in turn will melt more ice. Do you get the idea? This is a positive feedback mechanism, and change is being driven by the increasing amounts of heat being absorbed by the oceans, which continually melts more and more of the ice. I'm going to give you a second here to pause the slide, and what I want you to do is I want you to summarize this particular positive feedback mechanism. What happens in this situation? You can use the 3 arrows to help you step by step with what's happening here. Remember too, any time during these informational workshops, you can drag that slider right back and replay some of the things that I've said. So if you want to go back to my synthesis of what happens when the sun impacts the polar bear and the ice and the ocean water, pause it, step by step, write out your answers. That might not be a bad idea either. Go ahead and pause, give you a second to do that. And when I rejoin you, we're going to be talking about negative feedback mechanisms. Now, negative feedback mechanisms are different than positive feedback mechanisms. As a matter of fact, these are feedback mechanisms that actually work to maintain the system as it is. In other words, to maintain a status quo. Before giving you some examples that are geologic in nature, I want you to consider this example that we're all familiar with. So here in the picture, we've got a little cartoon of a little person. And this little person is trying to maintain their body temperature at 98.6 degrees Fahrenheit. And what we see happening here is we see this little person who is perspiring, whose heat is conducting away and radiating away from him in order to maintain his body temperature. So our bodies do this naturally and without us getting involved in it. And their desire is to maintain the status quo. So let's think about some negative feedback mechanisms that are geologic in nature. I'm going to ask you to consider a volcano. Now, we might think about a volcano on Hawaii, the big island of Hawaii, erupting, and wonder what is it that makes that volcano erupt? Well, beneath the volcano there's a magma chamber. And when the pressure in that magma chamber is high enough, it will cause the volcano to erupt. And it's that eruption that we could consider as part of the negative feedback mechanism. It's trying to maintain the status quo, the pressure within the magma chamber beneath that volcano. As I said earlier, we're going to be considering negative and positive feedback mechanisms along with the different spheres of Earth throughout the next several months. So don't feel bad if you're having a little bit of a tough time with this particular one. Let's move forward and talk about a quick mastery check. So here on the quick mastery check for this segment, you can see two pictures. These are pictures that are taken from the National Snow and Ice Database, NSIDC, and the pictures were taken many years apart. The top left corner picture was taken in September of 1979. The picture on the bottom right corner was taken in September of 2007. And if you look at the picture and trying to get an orientation, think about looking directly down on top of the North Pole of the Earth. So what you're looking at here is you're looking at the Arctic Ocean. You can see the gray parts of the images are land masses. The blue is the ocean. And the white is ice or sea ice or glacial ice sitting on top of the continent of Greenland. Now, for this mastery check, what I'm asking you to do is I'm asking you to compare the amount of sea ice from September of 1979 with the amount of sea ice in September of 2007 for the same locations. So these pictures of looking down on top of the North Pole are zoomed out to the same level, and you should be able to see that there is a different amount of sea ice between those two pictures. So what I would like you to do here is I would like you to use what you have learned about feedback loops, negative or positive, to explain the sea ice coverage or the sea ice extent in the Arctic Ocean as shown in these two pictures. You're going to want to initially decide whether this is an example of a positive feedback mechanism or a negative feedback mechanism. And once you've decided that, see if you can explain how the change took place. Rejoin me for the next segment. Welcome back to Segment 7 for an informational workshop, Chapter 1, An Introduction to Geology. We're coming to the last two segments of this chapter, our overview of our course of geology. And in the last two segments, we're really going to focus in on the solid Earth, the lithosphere or the geosphere. And this is really going to set us up for what we're going to be studying next, which will be the surface of the Earth and how it moves. So we'll be talking about plate tectonics, about Earth's interior, the interior layers of the Earth, about some of the natural resources found in Earth and on Earth, about earthquakes, volcanoes, and about movements around the crust that cause deformation, folds and faults of the Earth's crust. So in this cartoon here, we're really looking at cycling through the lithosphere. So again, we're talking about cycles that happen within the geosphere or the lithosphere itself. And what you can see here is you can see a progression in the solid Earth. So let's start out with the top of this cycle. Let's start with some existing mountains. Take a look at the center of the picture where it says erosion and transport. We're going to want to consider what it is that causes erosion and transport of Earth's materials. Now, later on in the winter, we'll be talking about weathering, mass wasting, erosion in depth, but for right now, we just need to consider what happens when some of the rock is broken down into smaller pieces of sediment. They move downslope, either through mass wasting or through a stream or river, and eventually may make their way out to some of the oceans or lakes, where they may be deposited and then buried. That burial and compaction and lithification turn them into our first rock type, which is known as sedimentary rock. In a minute, we're going to jump out and we're going to take a look at the different characteristics of each of the rock types. But for right now, we're going to move on through this cycle. Now, once a sedimentary rock is buried within the earth, it may be acted on by heat, pressure, or some chemically active fluids. And the heat and pressure and chemically active fluids may start to deform or metamorphose that sedimentary rock. They may change the rock. It may become a metamorphic rock. That's our second rock type. Now, if that rock is buried deeply enough so that it's hot enough to melt the rock, then the rock may become a magma. Once magma is returned towards the surface or exposed at the surface, erupted at the surface, it may cool and crystallize or harden into an igneous rock. That's our third type of rock in the rock cycle. And then the cycle begins over again. So let's move on and take a look more closely at the rock cycle. I'm going to ask you at this point to pause this video and to go ahead and click on the video that talks about the rock cycle. This will introduce you to some of the basics of the rock cycle and give you a better idea visually of what each of the components of the rock cycle is. So go ahead and pause the video and rejoin me after you have a chance to watch the rock cycle basics. Welcome back. I hope you enjoyed the video. Let's take a look at some of the characteristics of each of the three different rock types. Now, as we go through these characteristics, you're going to want to underline or highlight or circle some of the key terms that you think are particularly important as you consider the definition and characteristics of each rock type. These are going to help you when you do your quick mastery check in just a few minutes. The first type of rocks that we're going to consider are igneous rocks. Igneous rocks form when magma cools and solidifies. In the pictures here, you can see two different igneous rocks. The igneous rock in the top left corner is an igneous rock known as granite. Now, you might be familiar with granite from granite countertops, perhaps. Well, in fact, many of the countertops that are called granite countertops are not really granite if we classify them as igneous rocks. They are igneous, but they're different rock types. What's most important to notice in this picture is that you can see big crystals. You can see some crystals that are kind of rusty orange color, some that are kind of a charcoal gray or black color, and others that are a white color. Now, those big crystals that are evident in that rock tell us that that rock was cooled over a very long period of time. It cooled and crystallized beneath the Earth's surface and thus is known as an intrusive rock. Notice in the word intrusive the word in. Remember that as you think about it. It cooled and crystallized inside the Earth. The other picture shown here on the bottom right-hand corner is a picture of snowflake obsidian. This igneous rock formed in a very different fashion than the piece of granite shown above. This igneous rock, in fact, is a piece of igneous glass. There are no crystals in this rock. The magma that formed this rock cooled and solidified so quickly when it was erupted from a volcano that the ions in the magma did not have time to arrange themselves into a regular and repeating pattern required for crystallization. In fact, they simply froze in place, and that's why we call this an obsidian or an igneous glass. Because this rock was formed outside of Earth's surface, we call it extrusive. Think about the word exterior. An extrusive igneous rock is one that cools and solidifies at or above the Earth's surface. So here you have two main categories of igneous rocks, intrusive and extrusive, both of which were formed from cooling and solidification of magma. Now let's consider the next type of rocks, and that is sedimentary rocks. Sedimentary rocks are typically made up of materials derived from pre-existing rocks. So you can see the picture on the left here. As you look at this picture, what do you see? I'll give you a second to think about that. Why don't you jot down some of the things that you see? Now compare the picture of the rock on the top left, which is called a conglomerate, with the picture of the sedimentary rock on the bottom right corner. They look very different from one another. I'm sure immediately when you looked at the rock on the top left, you saw big pieces of gravel. And the picture on the bottom right doesn't contain pieces of gravel at all. In fact, the picture on the bottom right is known as a chemical sedimentary rock. Chemical sedimentary rocks are an entire class of rocks that form when material dissolved in water precipitates out of that solution. Now we'll be spending a week or so later on in the school year talking specifically about sedimentary rocks, and you'll get to know the different environments in which sedimentary rocks form, and you'll be able to recognize when a rock sample is seen, what kind of environment it formed in. Let's move on at this point to consider metamorphic rocks. Metamorphic rocks form when existing rocks are changed by heat, pressure, and/or chemically active fluids. You can see two different metamorphic rocks in this picture. Again, let's start with the rock on the top left corner. What is distinctive about this rock? I bet you said it was the pattern of black and white stripes that runs throughout it. And you're absolutely right. That pattern of black and white stripes is an example of a rock type known as a gneiss. It is a metamorphic rock that is what we call foliated. In other words, there is a preferred alignment of the mineral grains within that rock. The preferred alignment in this particular sample of gneiss is seen as the black and white stripes. Now that looks very different from the picture of quartzite in the bottom right-hand corner. This piece of quartzite is a piece of quartzite that came from Baraboo in Wisconsin, which is just a little bit north of Madison. Maybe you've had a chance to go up there and go camping or hiking. It's a beautiful place to go. And the bluffs at Baraboo are made up of quartzite, very similar to this piece here. Some of it that you might find there is a more purple color. This is a more red color. But this particular rock is known as a non-foliated metamorphic rock. So now you know a little bit about the three different rock types, igneous, metamorphic, and sedimentary. And it's time for your quick mastery check. So here's your mastery check. According to the rock cycle, explain how a sedimentary rock might form from an igneous rock, and then explain how a sedimentary rock could be recycled into an igneous rock. Thank you for joining me for this segment. This is the next to last segment. When you join me back again for segment 8, that'll be our last segment in chapter 1. Welcome back, and thanks for joining me for segment 8. This is the last segment of the informational workshop for chapter 1, an introduction to geology. Again, with this segment, it's really going to be setting us up for our study of plate tectonics, Earth's interior, earthquakes and volcanoes, and deformation. You're going to want to pay close attention to each one of the segments here within this section. We'll be talking about not only the surface of the Earth, but also the ocean floor topography and what we know about the continents. So here we start with a nice image of Earth's surface. It's a very colorful image, and there are also some letters on here. So let's take a close look at this picture. As you look at the picture, you notice greens, reds, oranges, of course the blue of the ocean. But let's think for a minute about what the colors on this particular image are telling us. What do they mean? Take a look at the legend below the picture. Compare what's on the legend with the image above. You're going to want to make a few notes here to the right of this picture about what the colors are showing us. Go ahead and pause this video while you make your notes. When you rejoin me, we'll be going on a tour of the Atlantic Ocean floor. We'll be considering some of the major ocean floor features then. So go ahead and pause here and write down what you think the significance of these colors on this image are. Welcome back. During informational workshops in the future, there will be times when you will be jumping out of the video or out of the workshop and going into some Google Earth files to look at some information or possibly to view some tours. Now, there are two different ways that you can access this particular bit of information. What you're going to be looking at here is you're going to be looking at and listening to a narrated Google Earth tour that explains the major ocean floor features with examples across the Atlantic Ocean floor. You can either go to the class webpage, Chapter 1, Introductory to Geology, and scroll down to the bottom of the page to the files that are attached to that page. Once you're there, you're going to look for a KML or KMZ Google Earth file. You can look for the blue and white globe logo, and the file name would be Atlantic Ocean Floor Features. If you download that file and then open it, it will open Google Earth. You can play the tour within Google Earth. That's how I'm going to ask you to do this in the future, but for this particular example, I'm going to go ahead and jump out, and I'm going to go into Google Earth and show you how you would play that tour. If you had downloaded the file and opened up Google Earth, you would find that your page would open up with a tour toolbar in the bottom left corner of the map view area. Here you see it has a play button. We're going to go ahead and play this tour, and we're going to look at the Atlantic Ocean floor features. Here we go.
Hey, I'm glad that you joined me for this tour of the major features of the ocean floor. Today we're going to start out on the continental shelf. You can recognize the continental shelf here using Google Earth by looking for the lighter blue colored pattern that parallels the coastline of the eastern United States. In the picture, you'll see some of the ecosystems, examples of them, that you might find along that region of the U.S. I encourage you to visit that website to delve in more deeply to that. Now, the continental shelf is really still continental crust. It is flooded. The height of it depends on where sea level is. The higher sea level goes, the more flooded that continental shelf becomes. The lower sea level is, the less flooded it is. The width of the continental shelf does vary from coastline to coastline. So you can see here along the interior western coast of Florida that the shelf is a little bit wider. And if we travel over to the western coast of the United States, you'll notice that the continental shelf along here is significantly narrower. Let's move along now to the continental slope. The continental slope is a slope, and it's a rather steep slope. It's the slope that moves from the continental shelf out towards the deep ocean basins. And it is typically a steep drop-off. We'll move along now to the continental rise. The continental rise is typically found at the base of the continental slope. It is a more gradual slope than the continental slope is, This area is typically covered in sediments that are derived from the landmass nearby, the continental shelf, and the continental slope itself. Now, at the base of the continental rise, you're going to find the deep ocean. That would be called the abyssal plain. The abyssal plain is the deepest portion of any of the oceans. It is characteristically very flat and covered in marine sediments. As you can see in this picture, there are not coral reefs here. It's too deep for that. It's dark, it's cold, it's flat, and it's covered in sediments. As we continue eastward across the Atlantic Ocean, we'll soon encounter a mountain range, an underwater mountain range. I encourage you to click on the video here in this place mark and watch the video. You'll be learning from a favorite science video performer, Bill Nye, and I think you'll enjoy it. Once you come back from the video, notice the topography, the increasing height of this mountain range, the mid-ocean ridge system. The last feature we're going to look at here as we consider the Atlantic Ocean is we're going to consider the topography of the entire Atlantic Ocean from the eastern coast of the United States all the way across the ocean to Africa. In order to do that, you will need to right-click on your My Places layer where it says Atlantic Ocean Topography. Once you've right-clicked, please choose Show Elevation Profile. This gives us a chance to learn more about the elevation of the land from the Atlantic coast across to Africa. And if we follow along here, we can see the elevation itself. So here we're on land at a height of about 775 feet. And as we move across the land and out onto the continental shelf, we come to the continental slope itself. You can see how steep it is. The continental rise, a little bit less steep, out onto the deep ocean, the abyssal plain. Finally, we climb up the mid-ocean ridge to the center of the mid-ocean ridge where seafloor spreading is actually taking place and creating new oceanic crust, pushing the Atlantic Ocean out wider and pushing North America away from Africa in this case. As we continue eastward and move back down the mid-ocean ridge onto the abyssal plain, we encounter the continental rise off of Africa, the continental slope, the continental shelf of Africa, and then we climb up onto the continent of Africa. Well, thanks for joining me for this tour. I hope you learned a lot. Bye-bye.
Now that you've had a chance to take a tour of the Atlantic Ocean floor features, you're going to want to make sure that you have the key features written down and you have some sort of definition for each of the features. So at this point, you want to go back, if you haven't done this during the video, and write down continental shelf, slope, rise, abyssal plain, and mid-ocean ridge system. And you want to write down a brief definition or description for each one of those features. Let's move forward to our last slide here before our mastery check. In this slide, we're considering what's happening not on the ocean floors or in the oceans, but what the segments of the land are looking like. So you can see in this picture something called a continental shield, also known as a craton. Continental shields or cratons are the stable interior regions of continents. In many cases, these tend to be the oldest portions of the continents. And we'll be talking more about continental shields as we talk about plate tectonics. But for the purposes of this slide, you'll want to notice where the continental shields, the orange areas, are, and where the other areas are, in this case, the belts of folded strata. Now, these are all part of the landmass, but take a look for some of the mountain ranges that you might recognize. In the western part of North America, can you find the Rocky Mountains? Along the western coast of South America, the Andes Mountains. What other mountain ranges do you recognize? So here compare the folded strata, the mountain ranges, with the continental shield or craton areas. So that's our last slide, wrapped up the whole chapter, and here's our last mastery check. For your last mastery check, you're going to list the major ocean floor features in order of increasing depth below sea level. So you'll start with the most shallow, and you'll go out to the most deep. And then, once you've done that, think for a minute about what is happening to the distance between London and New York City. And go ahead and explain what is happening to that distance and explain why. Good luck on your last mastery check. And congratulations on finishing Chapter 1. You made it! Great job!